Yeah, okay, so let's keep going about triangles and handle two handle attachments. So last time we saw that we had it from a two-handle attachment. We got a triple Heegaard diagram. And while we did it in the detail only for when we attach only one handle, and it's, but I mean, if there are more, I will leave it to your fantasy. Now we start, I will briefly describe how to go back. So suppose we have a triple diagram. I mean, there will be also base point for holomorphic curve reasons, but just for topology, this is superfluous. Then from this, we construct a four manifold as follows. We take, let's say, an hexagon that I draw like this. And then we label every second edge like E alpha. So this, I will call this, I don't know, something like delta bar. And that I could label this E alpha bar, E beta bar, and E gamma bar. So it's you should think of this as a compactification of the domain we use for when we do the fibration for the holomorphic curves. And now we call X alpha beta gamma will be this delta bar times sigma. So we multiply by the surface. And then we glue E alpha times H alpha, E beta times H beta, E gamma times H gamma. Well, H star is a handle body specified by the curve star. So it's the underbody where the curves alpha, beta, or gamma bound the disks inside. And here, of course, you glue this along the boundary. So the boundary of E alpha times H alpha is a sigma, and you glue it along E times sigma on this side. So in pictures, using the usual color code, it's here you add E alpha times H alpha, yeah, and we had, I forgot the bars here. Here we glue E bar beta times H beta. And finally, here we glue E bar gamma times H gamma. And if you see, this manifold has three boundary components. So these parts of the boundary has been capped off by the handle bodies, but this part of the boundary remains. And what you see this, here you see the handle body H beta attached to sigma times the interval attached to the handle body H gamma. So this is M beta gamma, this is M alpha beta, and this is M alpha gamma. So boundary of x beta alpha beta gamma is equal to m alpha beta union m beta gamma union m alpha gamma. And moreover, if you check the orientation, this has the boundary orientation. These two have the opposite of the boundary orientation. So in fact, we should put minus signs here. So of course, m alpha beta is specified by sigma alpha beta, and the same for the other two manifolds. So in the case if sigma alpha beta gamma comes from a two-handle attachment then m beta gamma is equal to S2 times S1, while S2 times S1 connected some G minus 1 times. If it's obtained by attaching a bunch of handles, you remove the number of handles here from the connector. But the point is, so this bounds m beta gamma, but not m beta gamma, anyway. This manifold, yes, let m beta gamma bounds D3 times S1. So we can glue D3 times S1, but boundary connected sum with itself G minus 1 times. So we glue this to m beta gamma, and the gluing is unique by a theorem of Lodenbacher-Penarou that says that every diffeomorphism of a connected sums of its 2 times S1s extends to the boundary connected sum of S2 times D2s. So there is a unique way to glue back the, I mean, up to diffeomorphism, there is a unique way to glue back this object. And with this, once we glue that, we obtain that should be checked. We obtain W, which is the cobordism obtained by adding the two handles. So I will not go that far in this direction, but just to say that this construction of the triple Heegaard diagram is not just something formal. I mean, it really describes in some sense the cobordism you are working with. A final remark before we move on is that spin-C structures on W, whatever they are associated. But here also there are essentially two plane fields up to homotopy. Two plane fields defined in the complement of a finite number of points and defined up to homotopy on the complement of a one complex. Are associated. So in the case of three manifolds, spin-C structures were associated to Heegaard-Floer generators. In the case of cobordisms, they are associated to homotopy classes of Heegaard-Floer triangles. So what I didn't introduce this notation, this terminology before, but so what is an Heegaard-Floer triangle will be a holomorphic map over this delta times sigma, satisfying all the properties I gave last yesterday. So essentially here again, like in the three-dimensional case, here we have a two-plane field which is defined outside of the, well, essentially this edge is times the critical point, the critical values of, no, the critical points of a Morse function on the three handle bodies. And then you modify this in the complement of the image of the disk and a section over the base point Z to define it almost everywhere. Yeah.
So I guess, so is there this notion of admissibility for such diagrams, which is more than just having three diagrams to be admissible?
Okay, that's. I think yes, there is. But it's exactly the same. You have a notion of periodic domain, and you want all periodic domain to have positive and negative coefficients. Ozsváth and Szabó uses something which is intermediate between the two, and he asks for every periodic domain which is a sum of double periodic domains to have plus or minus coefficients. But that poses problems when you want to sum over all spin-C structures. But you can get this stronger notion where you want triple periodic domains to have plus and minus coefficients without much effort. So I don't see a reason why you shouldn't ask that. So now let's see an example of a triple periodic domain, which is actually not a two-handle attachment, but it's it will be very useful in the following. So let's take alpha, beta, gamma with the property that beta I and gamma I are small perturbations of each other. And when I say small perturbation, I don't just mean I will say small perturbation for simplicity, but I don't just mean small. I also want to have the two to intersect in exactly 2 points. So it's the picture I've drawn many times. This is beta I in blue. And now gamma I in green, which is probably not so distinguishable from far away. I'm sorry. But I cannot change the color code, otherwise I will get confused. And you know, it's every paper in the last 25 years have been written with these colors, so it's not a good idea to start changing things now. Let's see if a different type of green fanculo. Merda. Oh, all this has been recorded, I suspect. So can we delete this part? Yeah, and then so then what is we have the usual generator theta I, and we call theta beta gamma the family of these. So moreover, suppose that we have some alpha curve. So the alpha curve will intersect these things somewhere. And we'll have an intersection x with with the blue curve, and since the green curve is a small translate, we'll have an intersection x prime with the green curve. So to every x in alpha I, well, alpha j intersect with beta I, there is canonical xi prime between intersection point between alpha j and beta I and gamma I nearby. So now I claim the following. The modular space of Heegaard-Floer triangles with vertices in x, theta, alpha, beta, and x prime, and we take I equal 0 and z equal to 0, and we take the cardinality of this is equal to 1. And again, the principle is like we did for strips by the Riemann mapping theorem. If you see a triangle in the diagram, there is a triangle, there is a holomorphic triangle. The proof is the same as we did for strip. It's even easier because we don't have to take care of reparameterizations because there are none here. 3 points on the boundary of a disk determine essentially the disk. So there's no automorphism left that can move, that can fix them. And moreover, in the target, again, you don't have translations anymore. So that's why you take I equal to 1 instead of equal to 0, I equal to 1. And so in here, the triangle that you see is this. Yeah, I should put the base point somewhere far away. But another important thing is that when we had strips, so imagine when you had a strip, you wanted, a curve which had global index 1. And here you already had index 1 in this piece. So if you had some non-trivial piece somewhere else, the index would be larger if you check with the index formula. On the other, so whenever you had a strip like this, for the two Heegaard-Floer generators to be connected by a holomorphic curve, they had to differ only. For a holomorphic curve coming from this strip, they had to differ only in these two intersection points, or other intersection points should be equal. But here you no longer have this because triangles have index 0, so you can have many separate triangles. Why say no? Okay. So here what you have, in fact, is that in your picture you have many So this blob signifies that here there is some topology that happens. It's not that I have parallel curves. And then you have, for every for every beta curve, for every pair of beta and gamma curve, you have one triangle like this. And the second part of the theorem is that there are no other triangles. And I'm not going to do it at the blackboard, but you can see that if you try to have something else, you are immediately forced to have to go to the base point region. Yes, I'm sorry. Okay, let me keep it to the game. Oh no, go on. I don't want to make you lose, so keep going, and especially if you're winning. If you're already losing, then that doesn't matter. But yes, and I mean, if with that shadow, it's the only one because of, I mean, the usual argument because for the strips. And what diagram? To what diagram? What is this diagram? Well, if you do the construction of X alpha, beta gamma, and then we take the union with the G minus 1, then what we get here actually, and it's not so hard to see, this is your manifold times 0, 1. So it's the trivial cobordism. So essentially what you have proved here is that the trivial cobordism induces the identity map. Okay, that's nice to know. Now the last thing I'm going to talk about is the surgery excess sequence. So let's say we have K in M a framed knot. The framing produces, well, that means that in the boundary of a neighborhood of K, we have two curves, a meridian and the longitude. The meridian, we call it mu, and the longitude lambda 0. So meridian and longitude. So we orient them such that mu and lambda 0 are an oriented basis of the neighborhood of K. Then we defined lambda 1 as lambda 0 plus mu, which means, well, essentially it means that the lambda 1 will be another curve in the boundary of the solid torus, such that its homology class will be the homology class of mu plus the homology class of lambda. And then we construct two new manifolds, one which I will call M0K, which will be M minus a neighborhood of K. So this is a manifold with boundary, and the boundary is a torus. And so we glue to the boundary a solid torus, D2 times S1, glued so that the meridian of the 2 times S1, so the boundary of the 2 times S1 is glued to the longitude lambda 0. To specify the resulting manifold up to diffeomorphism, it's enough to specify where we map, how we glue the meridian, because somewhat how we glue we glue the rest of the torus doesn't really matter up to isotropy. Not isotropy, sorry, up to diffeomorphism. And we define M1K the same, but with lambda 1 instead of lambda 0. Yes. So now the statement of the surgery excess sequence is the following. It's a theorem, as usual, from Ozsváth and Szabó, so I don't even write the names. There is an hexatriangle HF minus of M HF minus of M0K HF minus of M minus K such that F0 minus is the cobordism map for the attachment of a two-handle to K with Fred lambda 0. The other two maps are also cobordism maps of some slightly stranger cobordisms, but that's less important. And we have similar triangles for HF hat, HF plus, HF infinity. And I suspect for HF minus, HF infinity, you really need the completed version. I don't think you can do it with the uncompleted version, even if you have a strong admissibility. That's what is for the experts. But I really don't know, because I've never really worked with the minus and infinity. I've always worked with hat and plus. Okay, the proof of this is a long story, so I will be sketchy, and moreover, I will sketch it for HF hat, because for the minus or plus or infinity versions, you need some non-trivial gluing theorem, so you need really to do some analysis, while for the hat version is mostly a proof by pictures. An exact triangle means that the kernel of one map is equal to the image of the previous one. The point is, in algebraic topology, you talk about exact sequences, but in Heegaard-Floer homology, you don't have a degree. I mean, there's no well-defined degree over the integers. In some, so it's, and then you cannot talk about exact sequences. It's, there is a mod 2 degree, so your exact sequence becomes something that close up like in K-theory, if you know that. So that's. But here I'm even collapsing the mod 2 grading, so it's. Okay, so how you define that? First of all, we define, well, we take a Heegaard diagram, a quadruple Heegaard diagram. Sigma, alpha, beta, gamma, delta, and with the usual base point, such that and then I will do like, I will take some, okay, the properties are that sigma, alpha, beta, gamma, no, sigma, alpha, beta produce your original manifold M. Then you have, and also you have the following. You have a portion of the diagram that works like this. And you have beta like beta 1 like this. Gamma 1 like this. And now I need a color for delta. Let's do this. And this will be delta 1. So from this you can see that yes. So essentially what I'm drawing. Okay, no, I will tell you what how they are constructed. So the beta 1 is obtained by pushing the meridian to the Heegaard surface. Gamma 1 is obtained by pushing the longitude lambda 0 to the Heegaard surface, and delta 1 is obtained by pushing lambda 1 to the Heegaard surface. So beta 1 and gamma 1 are intersecting one point, and gamma 1 is homologous to beta 1 plus gamma 1, and it also intersects beta 1 and gamma 1 in one point. And then for the other one, they are all translate one of the other. So you have beta 1 like this. Gamma 1 like this. and delta 1 like this. So also you see that the diagram sigma alpha beta gamma also specifies the handle attachment from M to M0K. And here we have canonical intersection points theta beta gamma and theta gamma delta, which are obtained in the following. Between the alpha 1, beta 1, and gamma 1, but they all intersect in one point, so we have no choice. We have to take the unique intersection points. And here we take the usual canonical intersection point, so I guess it is these three in the top. Yeah, we also have theta, beta, delta. I'm not sure if you're going to use it. But. And the three maps will be obtained by counting triangles, and I will tell you which triangles we count. So F1 will be F alpha beta gamma of some entry tensor theta beta gamma. So it's this is the i.e. the cobordism map. Well, F alpha beta gamma means that it's the triangle map defined in terms of the diagram alpha beta gamma. So what we have defined yesterday. Then F2 is equal to F alpha gamma delta. So it's the triangle map for the diagram alpha gamma delta. Well, this, yeah. Wait. Because the labeling is wrong. Anyway, F2 is also a cobordism map, but for a cobordism we don't care about. Because, I mean, whenever you have a triangle map for a diagram with this property that two curves intersect in only one point and the other pair of curves intersect like this, this is a cobordism map. So this is also a cobordism map, but we don't care about this cobordism. At least not now. I mean, it can be useful sometimes to understand what it is. Theta gamma delta, and F3 is equal to F alpha delta beta theta gamma delta. And in fact, it would be probably better to put beta prime here and take beta prime a small perturbation of the beta. No, delta beta prime. Now we have three lemmas. We will see what can I prove before it's time to go to lunch. That Fi composed, no, Fi plus 1 composed with Fi is the zero map. So we do it. There is a kind of a symmetry in the diagram. So it's really enough if we do it for one of these three groups, and the same proof will apply to all other ones. So we do it for F2 compose F1. And what we do is we show that that the chain map underline this. So here the chain maps, here the maps in homology is homotopic to zero. So, and let's see what it is. Okay, F2 composed with F1 applied to some generator X is equal to F alpha beta alpha gamma delta of F alpha beta gamma X tensor theta beta gamma itself tensor theta gamma delta. And the claim, so the lemma, okay, this is sublemma. This is chain homotopic to F alpha beta delta of X tensor F beta gamma delta times theta beta gamma tensor theta gamma delta. What's the reason? Here I really have to go fast, so I hope you will believe me. But you do this by counting holomorphic Heegaard-Floer squares. So we define a square as, a square, so, but we write it with strip-like ends. We multiply by our surface F. We put on the boundary alpha, beta, gamma, delta times this segment, this portion of the boundary. Here we put alpha, beta, we put as input X. Here we put theta, beta, gamma. Here we put theta, gamma, delta, and we count holomorphic curves U from some Riemann surface to square times sigma with this So here in the output we put y with this boundary condition and asymptotics. And with that, we define and those will define some modular spaces x, theta, beta, gamma, theta, gamma, delta, y. But here there is something that happens. Okay, again, you have an index there. It's a long story, but there is something that happens that didn't happen before. Because now the square doesn't have a unique, a square which means the disk with 4 points in the boundary doesn't have a unique conformal representative. You can fix 3 points in the position you want, but the 4th point is still free to move, and different positions will give different non-homomorphically equivalent objects. So what you actually have to do, you have to count maps that goes to square times sigma, but for some position of the 4th point. So you are in some sense counting holomorphic maps not to a fixed manifold, but to a one-dimensional family of manifolds. And that's important because how the square can degenerate in two different ways. So I will color the edges of the square depending on the labeling of the boundary components. So where I put the alpha, I draw it red. Where I put the beta, I draw it blue, then green, and then yellowish. That degenerates in 2 ways. One, we can pinch here or we can pinch there, and it degenerates in 2 different triangles. So one way is this with red. No. What I'm doing? And this is f alpha gamma delta of f alpha beta gamma tensor theta beta gamma x tensor theta beta gamma and all tensor theta gamma delta. So the other way we degenerate is the following. And this gives f alpha beta delta of x tensor f beta gamma delta of theta beta gamma tensor theta beta delta. Moreover, we have two more degeneration. I mean, here I'm talking about how we degenerate the dimensional, one-dimensional moduli spaces. And the one-dimensional moduli spaces can degenerate as this, where this has zero dimensional, and plus you put strips on the side. But here you have a cycle, so you cannot really put so much strips on the side. And then you define Hi. And here I have really to be careful not to define the wrong. No, okay, here we define H3 of X as the sum of the number of points in the moduli space of index equal to -1 actually, and Z equal to 0 because I'm doing the hat version, otherwise you should put something else here. X theta beta gamma theta gamma gamma delta y times y. And then this very vague explanation shows that boundary H3 of X plus H3 boundary of X, these are the generation I have not drawn, where we take out strips like on the sides. This is equal to these two degenerations. So I will call this 1 and 2 equal to 1 plus 2. So finish the proof that these two maps are homotopic. So to compute this, the action of this in homology, we can compute the action of that in homology, and it's the same. Now we have the second sublemma, which is that f alpha gamma delta of theta beta gamma tensor theta gamma delta is equal to 0. So first I will do it on the torus. So I assume that the cipher, the genus 1, the Heegaard surface has genus 1, and then I will explain how to get to the general case. So the picture of that you in the torus is the following. It's what is that? Yeah. So when we draw this picture, you should observe that this picture is on the Heegaard surface, which is oriented as the boundary of the complement of the solid torus, of the neighborhood of the knot. And we have oriented mu and lambda 0, so that they were oriented by basis of the complement of a neighborhood of the solid of the knot, of the tubular neighborhood of the knot. So if you see some mismatch of orientation to what I said before, that's the reason. Here we are working in a surface which has a different orientation. And so I'm saying that, I don't know if it helps you now, but that confused me for a long time when I was trying to understand the long axis sequences. So it's so now, okay, we put the base point here. And now, you know, this is theta beta gamma. This is theta gamma delta, but all these points are identified, so this is also. And now you can see easily two triangles. So there are two triangles they call psi0 plus psi0 minus that belong to M I equal to 0 and Z equal to 0 between theta beta gamma theta gamma delta theta beta delta. And these are the only three intersection points. So that's all the triangles you're interested in. Remark there are also triangles psi k plus or minus such that between the same intersection point such that nz psi k plus or minus is equal to k times k minus 1 divided by 2. How do you see them? Well, you go to the universal cover and you take larger triangles. So it's a triangle that here, for example, it goes like that, but then it continues, blah, 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 blah. So you will have this, for example, psi0 will have multiplicity 1 here and 0 elsewhere, and psi1 will have multiplicity 2 here and 1 elsewhere, and so on. But those are necessary if you want to do the excess sequence for the minus version. But now, for simplicity, we stay on the hat. But that's just to say, this is why this works also for the minus version. Now, what happens if we don't have an excess, if we don't have a genus 1 Heegaard surface, but something bigger? Well, which means that for how we chose the diagram, you see there, our diagram is a connected sum of this portion plus something else that lives here. And on this something else, what you see is this. But the important part is that if we work on the hat version, and here it's where the hat version is much simpler, we are not allowed to cross Z. So every triangle. So, but in this sense, we say that sigma alpha, beta, gamma is equal to let me finish writing, otherwise it will confuse me, and then we ask. So our diagram is a direct sum, a connected sum of two diagrams. This one, E alpha 1 beta 1 gamma 1 is what you see here. And sigma prime alpha prime beta prime gamma prime is something here where all curves look like this. Plus the alpha will do something. Sorry, or what did you, what was?
I'm just trying to, so I guess psi0 and psi0 plus or minus are those two shaded things?
Yes.
But if I look at psi1, I would also get nz equal to 1.
Yes. Psi1 will have an...
nz equal to 0, I'm sorry.
Psi1, no. Because Psi1 is goes like this. Pa, 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 pa.
Okay, so then maybe it's k2 plus 1 or something?
Maybe.
Actually, my real question was what is psi1? You say psi1 is...
You should write this in the universal cover. So now you take this. And let's say and you start like this, you go to a larger thing. something that you wrap around the top. So, okay, let's go back. We have a connected sum. We are not allowed to cross the boundary point, the base point, and the base point in the connected sum region, so, which means that every triangle in M theta alpha beta theta beta gamma and whatever we put here splits as a disjoint union of triangle which projects to sigma prime and a triangle which projects to E. But the triangle which projects to E, this can be either psi minus, psi 0 minus, or psi 0 plus. And any of those goes in the sense that whenever we have a triangle that projects here, we can add either this or that and obtain a triangle on sigma. So what it means that for every triangle that you had in this part of the diagram, and you can prove that you have only one, but we don't care, you actually have two in the bigger thing because it can be completed with two choices here. This means that the number of points mod 2 of I equal to 1 and Z equal to 0 moduli space from theta beta gamma tensor theta gamma delta theta beta delta, this is equal to 0. And that implies that the map F alpha, F beta gamma delta of theta beta gamma tensor theta gamma delta is equal to 0. So, okay, now we have that the same argument can be done actually for all three groups, and it's exactly the same. The name of the curve will change, but the pattern will be the same. So we have now that the composition of two consecutive maps is 0, but that's not yet an exact sequence. So, okay, so I could stop here if you want. The interesting part is what is left out. But anyway, you have to work a little bit more to get exactness. Of course, we are feel free to ask how we prove exactness, but that will probably go up to noon. So it's.
I think yeah. So some of us have trained, I guess.
Uh-huh.
So let's stop here, and we can probably go on during the tutorial.
Yes.
So let's think, Paolo.
What? I will. I mean, I'm not sure if I can arrive at 4 sharp. No, it starts when, the tutorial? At 4 or 3:30? Okay, I'm not sure if I can arrive at 3:30 sharp, but eventually I will arrive and I will stay until up to the end. So I have some paperwork to do. So it's I don't know. First I have to do that, but then I will go to the tutorials and stay up to the end. Yeah, sure. Yeah, okay.
So I would just like to say that if some people want to have more choice as the restaurant, so maybe it's time for a 3-minute break. Because if some people wanted to use and we can go on as we wish. Is that okay?